Welcome. In this video, we are going to review the AutoInt paper. So that's a very interesting paper focused on making nerve faster at inference time. The tech behind it is very interesting, and that's from a very good and very great researchers from Stanford University. So maybe we can start by having a look at figure 2. So basically, when we solve an integral with the integrand that are integrated, and basically the value of this integral is equal to the to the integral of the integrand from minus infinity to b minus the value of the integrating from minus infinity to a, and basically there is of course there is a relationship between between phi and psi, but so basically what they suggest is instead of learning, so basically when we solve nerve, usually we approximate psi by a neural function approximator, so usually neural network. But then that means that at inference time we need to solve again this integral, which is a difficult task. And what they suggest is instead let's model phi directly. So let's model this function so that at inference time when we need to solve this integral, we can just evaluate the neural network or the function approximator and make this operation, which is very cheap, as opposed to solving the integral. So far so good. At inference times it makes sense, but during training we cannot supervise this function directly, so we need to supervise psi. And in order to supervise psi, as psi is the derivative of phi, we can compute it easily. We can derive this function, and to do that we can do that very easily using like automatic differentiation programs, which is usually what we use when we train neural network. So basically the idea is to model the integral network phi, and then to build the grad network by just differentiating it. And therefore then that means that during training we can evaluate psi, and we can train it. And again, then during inference, it's very simple to evaluate the integral. It just consists in evaluating or running the integral network using the forward pass of it. Okay, so we've discussed that. Basically, so we model the integral network, but we train the grad network that is derived directly from the integral network. We can compute that just like automatically using automatic differentiation, but in the paper they compute it manually because it's more efficient. But we could just use automatic differentiation for that as well. That will consume more memory and be less efficient. So for example, during training we differentiate the integral network to get the grad network. But during inference, we just use the integral network directly, and that allows to have up to 10 times speed up. Well, more than 10 times speed up. Okay, so the principles, we explained the principles. Basically, of course, there is a clear link between the integral network and its grad network. And they leverage that. The grad network can be, again, built directly from the integral network, either by doing automatic differentiation, or to build it directly manually, or by using some custom code to do it. They have some example in computed tomography that also involves like solving the tomography integral, but we are more interested in neural volume rendering in that video. So basically they show that the volumetric rendering equation can be written like this, which is, they explain that in the supplementary. So it's a different formalism than the one that we're usually using when we train a nerve. The explanation is pretty clear in the supplement. By taking some limits, basically this reduces to the equation we usually use when we train nerve models. And then so that means that you can use the standard nerve way of training things during training, but then at inference you can evaluate each sub integral directly just using the just by evaluating the integral network at ti on ti minus 1. So here we have a trade-off, which is n. So basically, n means for evaluating the color of a pixel, we will split the space in different regions. Well, they call that sections. And therefore, for each sections, we are going to evaluate the integral network to get the color on density on that section. And basically, the more section we use, the more the better the accuracy. But of course, the slower the model. But then we can play a bit with n to have better accuracy or better speed. At inference time, we only need to evaluate the integral network at the boundaries of those sections. But during training, we sample rays within the sections, the same way we sample points along the rays with nerve in order to train the gradient network. I think they have some metrics where they compare the number of sections. So here we see 2 sections, 4 sections, 8 sections, up to 64 sections. And we can see that, for example, going from 32 to 64 sections, there is a marginal improvement. We don't have. We could have a look at if they mention speed somewhere. Here they mention memory on speed. So for example, you can see going from 8 to 16 section, you gain a bit less than half a decibel in a PSNR. You gain a bit more by going to 32. The memory is roughly constant, but the runtime, you see a drastic loss in, it's linear with n, the runtime, which is expected. So I think that's it for this paper. So focused on making nerve faster, very interesting, like improving the way not the way the rays are sampled, but allowing to sample fewer rays along the rays. So that can be not really sampling fewer rays along the ray, but reducing the number of function evaluator or the number of function evaluation along each ray for each pixel, and therefore that can be combined with other methods that are also making nerve faster. So very interesting. I really like the maths and the idea behind this paper. If you're interested in nerve, do not hesitate to subscribe and leave a thumbs up if that video was helpful to you.